Before we launch into this mind-blowing journey through humanity's struggle to understand the universe, hit that subscribe button and smash the like button. It really helps this channel keep exploring the cosmos with you. Now, fasten your seatbelt, because we're going from ancient myths to the edge of infinity. In 2017, an international team of astronomers announced something that made the front pages of every science outlet on the planet. They had discovered 7 Earth-like planets. Not one, not two, 7 rocky worlds, similar in size and composition to our own, all orbiting a single star. And that star is only 39 light-years away. That's practically next door, cosmically speaking. Astronomers are confident that with the new generation of telescopes, they'll soon be able to tell whether any of those planets have atmospheres, and whether those atmospheres contain water vapor. Because water is the universal solvent, the liquid in which the organic molecules that make up DNA can mix and dance. Scientists may soon prove that the conditions for life are common throughout the universe. It's even possible that in the near future we will find the holy grail of planetary astronomy, a true twin of Earth orbiting another sun. Around the same time, astronomers found another Earth-like planet, Proxima Centauri b. It orbits the closest star to our sun, just 4 light-years away. That's literally our cosmic neighbor, and it sits right in the habitable zone where liquid water could exist. All these discoveries are just a few new entries in a vast encyclopedia that now lists more than 5,000 confirmed exoplanets. 2 years later, the world's media reported another breakthrough. Scientists had finally captured an image of a black hole. That famous photograph, a glowing red ring of gas spiraling into a dark shadow at the center, was seen by billions of people. You've probably seen it too. Black holes had been mathematically predicted from Einstein's equations more than 100 years ago, and that image proved that these once unthinkable objects really do exist out there. By the way, that particular black hole is monstrously huge, 6 billion times more massive than our sun. To me, the picture looked like the Eye of Sauron from The Lord of the Rings, except this eye is real and it's the size of our entire solar system. To capture that unique image, astronomers created a virtual telescope as large as the Earth, combining data from 5 different observatories around the globe. But honestly, all that pales in comparison to the James Webb Space Telescope, launched at the end of 2021. Within its first year of operation, it sent back images of distant galaxies that made astronomers' jaws drop. Look at this. This is what the universe looked like more than 13 billion years ago, shortly after the Big Bang. We're seeing the very first galaxies, young, misshapen, still forming. Their light has been traveling to us for several times longer than our planet has existed. And here's another image, just as fascinating: the Ring Nebula, the remains of a dying star that has shed its outer layers. Only thanks to Webb's incredible sharpness have we seen the finest details, the swirls and curls of gas. For the first time, astronomers are watching a star die moment by moment. And this is only the beginning. Webb will keep working for many years, regularly showing us new corners of the universe. And there are dozens of other observatories around the world and in space, all tirelessly scanning the sky, gathering gigabytes of data to piece together a single picture of reality. That picture is breathtaking. Our universe is incredibly diverse, from the tiniest particles to giant clusters of galaxies, from the deserts of Mars to oceans that might teem with life on exoplanets. But here's the most amazing thing. All this grandeur obeys the same laws of physics. Laws that the human mind is capable of discovering and understanding. It's astonishing how far we've come, from primitive myths to modern astrophysics. By studying the cosmos, we understand not only the universe around us but also ourselves. We are all children of the stars, literally. Every atom in our body was once forged in the nuclear furnace of a star. But how did humanity begin to build a picture of the world? Starting from simple observations. That adventure of human thought is what we're going to trace today. From the primitive astrology of ancient civilizations to the latest theories of the origin and evolution of the universe. Let's start with a journey through time. Imagine yourself as a resident of ancient Greece. If you had no knowledge of the world around you, how would you perceive the universe? You stand on solid ground, which is flat, apart from mountains and valleys. Above you is a blue sky with the sun, the moon, and stars. Your life unfolds among wild nature forests, steppes, rivers, mountains. Every day, a blindingly bright circle rises in the eastern sky, the sun. It gives the Earth light and warmth, setting the rhythm for all living things. The sun follows its eternal path. It rises to its zenith and then sinks below the horizon. The solar cycle lies at the heart of the biological clock of every creature on the planet. When the sun sets, the world plunges into darkness and cold. In the sky, the stars appear, and their patterns remain unchanged night after night. Observant people grouped them into memorable constellations to help them navigate. 5 particularly bright stars change their positions, tracing strange loops across the sky. They are called planets, named after powerful gods. Mercury, Venus, Mars, Jupiter, and Saturn. All these phenomena, so familiar to modern people, once hid deep mysteries. The natural cycles were not random, they were rules. Spring always followed winter, never the other way around, year after year. With the development of speech and abstract thinking, people began to delve deeper into the nature of the world. At first, they simply noted sequences of events. After sunset comes night. But then came a flash of insight. It gets dark because the sun has hidden. Day follows night not by chance, but according to a strict celestial schedule. In ancient times, it was believed that the world consisted of 4 elements: earth, water, air, and fire. In China, they added wood and metal. The mixture of these elements supposedly created all substances, and different gods controlled them. It was logical to assume that the Earth was a flat disk covered by a dome of the sky. In some places, the disk was filled with water, but there was solid ground beneath the water. Rain sometimes fell from the sky. Obviously, there was a supply of water up there. The sun and moon moved across the sky, and the stars were like holes in the celestial vault, letting in light from outside. The same picture of the world was described in the Old Testament. God created a firmament separating the waters below from the waters above, and on the firmament he placed the sun, the moon, and the stars. Few people disputed these ideas because they matched the visible picture. Why not? In ancient times, it was also commonly thought that the massive Earth rested on some supports: elephants, turtles, bulls, you name it. The movement of these creatures explained earthquakes. The Earth might float in a world ocean or be chained to the sky. A Muslim myth pictured a complex structure of an angel, a bull, a giant fish, and the Earth resting on them. In Slavic legend, the supports were oaks and whales in a sea of fire. This is an important point. The authors of cosmological concepts could have piled support upon support, but at some point the chain had to stop, otherwise they would have had to multiply supports to infinity. Sooner or later, thinkers realized that divine will was necessary. But if divine intervention was needed anyway, why not just have the Earth float in space without any props? The first to come up with that idea was the ancient Greek philosopher Anaximander in the 6th century BCE. In his model, a cylindrical Earth simply hung motionless at the center of the cosmos. The explanation was brilliantly simple. The Earth has no reason to move in any direction, since it is already at the center. Realizing that a huge Earth with all its continents and oceans could rest freely in empty space was a massive intellectual breakthrough. No matter how absurd this idea might have seemed to the average person, it was still more reasonable than infinite elephants on turtles. Curiously, Anaximander was also the first to suggest that celestial bodies lie at different distances from the Earth. According to him, there was a primordial substance, the apeiron dash, which separated into a cold core and a fiery shell. The heat of the shell broke it into several rings. In the nearest ring were the stars, holes through which the fire was visible. In the next ring was a larger opening, the moon. In the farthest ring was a hole the size of the Earth, the sun. At the very heart of the cosmos was the Earth, shaped like a flattened cylinder. Its surface was covered with a wet primordial silt, and in that silt a miracle occurred. The first living creatures were born. They resembled fish and evolved into other beings, eventually giving rise to the first humans, who left their fishy cradles. This was essentially the first geocentric system of the world. Of course, it was nothing more than a beautiful tale, but for its time it was incredibly cool. It dispensed with gods, explained the Earth, life, and humans. Alas, there was no way to prove or disprove the hypothesis. Anaximander's students, Anaximenes and Heraclitus, developed the idea, adding new details. They were united by a materialistic view of the universe. The world explains itself without reference to gods. Heraclitus, for example, declared that the main sources of knowledge are sight and hearing. We cannot skip the cosmology of the great mathematician Pythagoras in the 6th century BCE. The Pythagoreans believed that the cosmos is ruled by mathematical harmony. Pythagoras discovered that the sounds of an octave are produced when a string is divided in ratios of 1 to 2, 2 to 3, 3 to 4, and so on. Musical intervals are given by simple numerical ratios. For Pythagoras, this meant that pure mathematics lies at the foundation of the cosmos, hence his famous saying, "All is number." What did the world look like to Pythagoras? At the center of the universe blazed a mysterious central fire, Hestia dash. Around it orbited the Earth, the Moon, the Sun, and the 5 known planets. Between the Earth and the central fire circled a mysterious Antichthon, a counter-Earth. The celestial bodies were attached to giant crystal spheres nested inside one another. Rotating at different speeds, these spheres carried the planets and stars and also produced a kind of music, each sphere its own note. This harmony of the spheres we cannot hear only because we were born into it and perceive it as silence. Of course, Pythagoras' system was also speculative. The spherical Earth, the crystal spheres, the counter-Earth, all just guesses. But for the first time, the planets were listed in the correct order, and it was shown that the Earth is not the center of the world but merely one of the celestial bodies orbiting something else, even if that something else was not the Sun. His followers even explained the alternation of day and night by the rotation of the Earth. That's practically Copernicus, 2,000 years before Copernicus. As we can see, 25 centuries ago, the best minds of humanity had begun to seriously think about the structure of the cosmos, purely speculatively, without experimental support, but they already made insights far deeper than tales of the Earth on whales. What unites all these theories of the ancient world, from the biblical to the Pythagorean? You've probably guessed. They were mostly invented. Yes, they were based on observations, but much was made up. There is no solid heavenly vault, no crystal spheres emitting music. So what allowed humanity to distinguish truth from fiction? It seems to be the birth of critical thinking, upon which the scientific method grew. People began to analyze their own ideas, asking themselves, why do I think this? Can I think differently? What if lightning is not the wrath of Zeus? Critical thinking became the engine of civilization. Consider ancient Egyptian and Babylonian texts. They contained nothing like mathematical proofs. The very concept of proof was absent. Proofs appeared in ancient Greece more than 2,500 years ago, probably because of the rise of democracy. In debates among equal aristocrats, logic and different points of view were required, along with arguments to back them up. The one with better arguments won, not the one with a laurel wreath on his head. Transferring the practice of proof to mathematics led to the creation of theorems. Thales already proved the statement about the equality of angles at the base of an isosceles triangle. Mathematics was considered a noble pursuit for an elite circle. No wonder the Greeks soon developed all of geometry. In the 4th century BCE, Aristotle was one of those who applied the scientific approach to the structure of the universe. Studying the moon, he understood the nature of its phases. The moon is a sphere onto which sunlight falls. Observing the moon covering Mars, Aristotle concluded that the planets are farther away than the moon and the stars farther than the planets. But that's not all. Aristotle also had 3 arguments for the sphericity of the Earth. First, when a ship sails away from shore, its lower part disappears first, then the middle, and only then the sails. This is only possible if the sea surface is convex. Second, during lunar eclipses, the Earth's shadow on the moon is always round. Third, as an observer moves north, the North Star rises toward the zenith, again indicating the curvature of the Earth's surface. Based on these facts, Aristotle logically and flawlessly proved that the Earth is a sphere. He was wrong in thinking that the Earth is the center of the universe, but he based that on observations too. If the Earth moved around the Sun, he reasoned we would see a shift in the stars. But the stars are so far away that those tiny shifts could not be measured until the 19th century. In Aristotle's time, the immobility of the Earth seemed proven. For centuries later, Aristotle's ideas were embodied in the system of Ptolemy. Ptolemy asked, how can theory be reconciled with what we actually see in the sky? He developed a complex system of epicycles, circles upon circles. Planets moved on small circles whose centers moved on larger circles, and so on. The radii and speeds were adjusted so that the predicted positions matched observations as closely as possible. To get a good fit, he had to pack in a lot of circles. Despite its artificiality, Ptolemy's system worked remarkably well. It could predict planetary positions up to a year in advance. Ptolemy did not simply assume the Earth was stationary. He was a brilliant scientist who knew about centrifugal force and inertia. But without precise formulas and experiments, he couldn't evaluate their effects. He reasoned, if the Earth rotated, then falling objects and clouds would lag behind due to inertia, and a stone dropped into a deep shaft would hit the wall. It took 1,700 years for the experiment of Benzenberg to show that such an effect does exist. It's just extremely small. Ptolemy's system was not based on guesses but on strict logic and observational data, which distinguished it from previous world pictures. In the end, science itself, testing and improving itself, would later refute that model. But until then, Ptolemy's system dominated European thought for 15 centuries. From the observations of the Greeks 2,000 years ago, it followed that the center of the world is a spherical, motionless Earth. Did no one question that? There were some bold thinkers. For example, Aristarchus of Samos, long before Ptolemy, proposed a method to measure the distances to the Sun and the Moon. Observing the Moon at first or last quarter, when we see exactly half its disk, Aristarchus reasoned that the angle between the directions Earth-Moon and Moon-Sun is nearly 90 degrees. Therefore, the ratio of the distances Earth-Moon to Earth-Sun equals the cosine of that angle, which can be measured. His measurements gave that the Sun is about 20 times farther than the Moon. Actually, it's 400 times. But for those methods, it was a decent estimate. And since the apparent sizes of the Sun and Moon are roughly equal, the Sun must be about 20 times larger than the Moon. Comparing the size of the Earth's shadow on the Moon during eclipses, Aristarchus calculated that the Earth is about 3 times larger than the Moon, close to the truth. Thus, the Sun is larger than the Earth by a factor of 6 in diameter, meaning hundreds of times in volume. The colossal size of the Sun led Aristarchus to the idea of a heliocentric system. It was more logical that the enormous Sun should be at the center, with the smaller Earth revolving around it. Additional evidence came from changes in the brightness of Mars, inexplicable in the geocentric model. As for the lack of stellar parallax, Aristarchus argued that the stars are unimaginably far away, and he was absolutely right. But his hypothesis could not yet compete with the elegant, detailed system of Ptolemy. At the end of the 5th century, after the fall of ancient civilization and the onset of the Middle Ages, the understanding of the universe not only failed to develop but actually lost many earlier achievements. The new spirit of the times was different. The need to explore the world beyond the Bible was questioned. The works of ancient thinkers were often destroyed. The Library of Alexandria was burned to the ground along with thousands of priceless manuscripts. Want to ask an uncomfortable question? Welcome to the stake. The main picture of the world for Christians in the 6th century became the primitive scheme of Cosmos Indicopleustes, a flat, rectangular Earth surrounded by walls and covered by a solid heavenly vault. Night falls when the sun hides behind a high northern mountain. The idea of a spherical Earth was at first ridiculed. How could people on the other side walk upside down? Later, Aristotle's teaching was selectively accepted by the Church. The idea of the central position of the Earth as God's main creation suited biblical conceptions. But what about Aristotle's method of studying the world through observation? That was forgotten. The treatises of scientists were simply memorized without analysis or criticism. Independent thinking was discouraged and under threat of accusations of heresy. Unsurprisingly, during the entire medieval period in Europe, not a single major astronomical discovery was made. Only in the 15th century did astronomy finally stir from its stagnation. And guess who had the courage to revive the heliocentric idea? Priest. Imagine Nicholas Copernicus, sitting in a monastery, studying ancient folios, and at some point it dawned on him, oh my God, it all fits together. The sun at the center, the Earth revolving around it. The Earth also rotates on its axis. That immediately explained the looped motions of the planets. But Copernicus did not rush to shout his discovery from every corner. Why? He spent 40 years refining it, trying to leave no loopholes for criticism. He followed Ptolemy's structure but used fewer epicycles combined with eccentrics. Most importantly, he swapped the positions of Earth and Sun, making the latter the center of the system. The planets were attached to transparent spheres nested inside one another. All the stars lay on the largest sphere surrounding the solar system, like wallpaper on the walls. Copernicus's work was a dense tome, not easy reading, and his predictions were actually less accurate than Ptolemy's. But his main ideas quickly spread across Europe. It was a true breakthrough. Copernicus himself did not live to see the publication of his work in triumph. The transition to a new picture of the world, later called the Copernican Revolution, was truly revolutionary. Just think, the Earth was moved from the center of the universe to a backwater, becoming just one of many planets. Humanity lost its privileged position in the world. What a blow to our self-importance. The transition took many years and was not easy. It seemed that no new evidence for heliocentrism had appeared. All of Copernicus's arguments had been made before, for example, by Aristarchus. The Catholic Church initially reacted calmly, seeing heliocentrism as just a convenient computational tool. But soon it caught an unpleasant whiff of heresy in the idea of moving the Earth from the center of creation. A particularly fiery advocate of Copernicus's ideas was Giordano Bruno, who openly criticized church dogmas, and that, let's say, poured oil on the fire. In his view, the universe is infinite and filled with countless worlds like our solar system. Stars are distant suns around which planets orbit, possibly inhabited. Such bold ideas of the plurality of worlds could not please the Church. The outcome was sad. In 1600, Bruno was burned at the stake. Copernicus's On the Revolutions of the Heavenly Spheres was placed on the Index of Forbidden Books in 1616. It seemed heliocentrism was doomed. But then progress intervened. In 1609, Galileo Galilei, inspired by a Dutch spyglass, built a telescope and pointed it at the sky. Discoveries poured out one after another. Galileo found that Venus has phases like the Moon, which means it orbits the Sun. Jupiter's moons clearly orbited that planet, not the Earth. These were undeniable proofs of the heliocentric system. So why did Copernicus's idea eventually win despite the power of the Church? It seems it was another shift in the spirit of the times. The life of Europeans in the 17th century was full of hardships and upheavals. The familiar medieval order was collapsing, religious wars raged, the plague was rampant. Feeling like the pinnacle of creation, living in an ideal center of the universe, was rather unpleasant for a land tormented by disasters. The Earth seemed a godforsaken periphery, far from perfection. The place at the center of the universe better suited the sun, an ideal, eternal source of light and warmth. Thus, gripped by crisis, the public consciousness was psychologically ready to accept heliocentrism. However, a clear and logical picture of the world still faced one more obstacle: the idea that planets move in perfect circles at uniform speeds. To explain the deviations from this, ancient and medieval astronomers had built unthinkable tangles of epicycles and eccentrics. Even Copernicus could not completely abandon them. Only at the beginning of the 17th century did the brilliant Johannes Kepler, analyzing the precise data of Tycho Brahe on the motion of Mars, discover his famous laws. It turned out that planets move around the sun not in circles but in ellipses, and their speed is not constant. The closer to the sun, the faster they go. Kepler's laws described the observed motions with exquisite accuracy, without any epicycles, confirming and complementing Copernicus's heliocentric system. No wonder they are often called the final chord of the Copernican revolution. But the crown of that revolution was the idea of the infinity of the universe. Nicholas of Cusa in the 15th century had already argued that in a limitless cosmos there can be no absolute center, neither Earth nor Sunday. He allowed the existence of countless worlds. Giordano Bruno developed these ideas, declaring that only an infinite universe with an uncountable number of starry worlds could correspond to the greatness of the Creator, and many of those worlds might be inhabited. Imagining infinity is easier than it seems. Since childhood, we encounter it. There is no largest prime number because you can always add one. There is no cosmic wall with a sign "end of the world." No matter how much time passes, the next moment always comes. Personally, I find it harder to imagine a finite universe than an infinite one. Such a picture of the world broke the old notions of solid celestial spheres and a fixed dome of stars. An infinite space needs no material support. Critical thinking showed, if the Earth can float freely in space, why can't other celestial bodies do the same? In the earliest world pictures, divine will had to be invoked simply to break the infinite chain of celestial spheres or cosmic turtles. So too here, no matter how much the Church tried to silence free thought, the idea of a boundless universe inevitably grew in the minds of thinkers like Cusanus and Bruno. People had long asked, what forces move the celestial bodies? Some thought the lights moved of their own accord, being alive. Others thought they were guided by spirits, angels, or gods. But as centuries passed, all those supernatural explanations somehow lost their persuasiveness. People became accustomed to the idea that impersonal natural forces, the laws of nature, operate in the world. Kepler, who discovered the laws of planetary motion, suggested that a planet's speed decreases with distance from the sun because the sun contains the source of the moving force. William Gilbert, a contemporary of Kepler, studied magnetism and proposed that the Earth is a giant magnet. The behavior of a compass needle pointed to that. In the early 17th century, it was even discussed whether the Earth rotates due to magnetic forces and whether the moon affects the tides through magnetism. In 1609, Kepler went further. What if the sun is also a magnet, and its rotation creates a vortex in the ether, causing the planets to move around the sun more slowly the farther they are? Descartes went even further, imagining the universe as a set of ethereal vortices with stars at their centers. Although these ideas turned out to be wrong, it later was confirmed that the sun indeed has a magnetic field that rotates with it, but the planets do not move because of that. The true nature of the forces governing the universe was revealed by the genius Isaac Newton. He realized that the force holding the moon in its orbit and the force pulling an apple to the ground are the same force. If the moon suddenly stopped, it would fall to Earth just like an apple. It's just that the moon has a huge orbital speed, so it constantly misses the Earth. Could we turn an apple into a moon by giving it high enough speed? Newton understood, yes, easily. By continuously falling, it would circle the Earth and become its satellite. In a famous drawing, Newton depicted a cannon on a high mountain, firing horizontally. If you increase the speed of the cannonball, it will land farther and farther away. At a certain speed, the ball will never fall. It will circle the Earth in a circular orbit. That speed is called the first cosmic velocity. If the ball is fired faster than that, it will move in an elongated ellipse. With increasing speed, the ellipse becomes more stretched. When the speed reaches the second cosmic velocity, the ball will leave Earth forever. Thus, Newton discovered the universal law of gravitation. Gravity is noticeable only when at least one mass is huge, like the Earth's, but it acts between any bodies, following a precise mathematical formula. Studying the moon's motion, Newton derived this law mathematically, and it turned out that all three of Kepler's laws are simple consequences of Newton's law. Gravitational theory worked like clockwork, allowing extremely accurate calculations of planetary and spacecraft orbits. Comets played an important role in confirming Newton's theory. Analyzing their motion, astronomer Edmund Halley established that comet trajectories are highly elongated ellipses that cross planetary orbits. If crystal spheres existed, comets would inevitably smash into them, but nothing of the sort was observed. Thus, comets shattered the crystal spheres to pieces. By the 18th century, the educated part of humanity had accepted a new picture of the world. The universe as an infinite space filled with countless stars and planetary systems like our own, governed everywhere by the same law of gravity, with time flowing identically everywhere. Of course, puzzles remained. For example, why do all planets orbit the sun in the same direction and nearly the same plane, unlike the chaotic motion of comets? Unable to explain this, even Newton resorted to the idea of divine design. As telescopes improved, astronomers obtained more and more data about distant objects. And what did they see? Basically, nothing seemed to change globally. On Earth, seasons changed. Planets and comets circled the sun. Stars twinkled in the distance. The cosmos looked stationary, what physicists call unchanging in time. Individual stars died, but new ones were born to replace them. Many thought it would always be that way. The universe would remain forever unchanged. Of course, medieval thinkers had allowed that the cosmos might evolve, but that idea was not fashionable. Astronomers mostly tried to understand the properties of celestial bodies based on the assumption of an unchanging universe. To figure out the structure of the cosmos, we needed to know the distances to stars. The method had been known since antiquity. If you measure a star's position many times over a year, the Earth's orbit around the sun will cause it to trace a small ellipse, the annual parallax. The smaller the ellipse, the farther the star. Alas, for a long time no one could measure parallax. Not even great astronomers like Kepler and Herschel. Stars stubbornly remained motionless. Geocentrists rejoiced, "Aha! Proof that the Earth does not move." But Copernicus and his followers rightly replied, "No, the stars are just incredibly far away." Only in 1838 did Friedrich Bessel, using the precise Fraunhofer telescope, finally measure the parallax of a star. It turned out to be at a distance of 10 light-years. Hang on tight, about 90 trillion kilometers. Soon similar measurements were made by Struve and Henderson. Thus a breach was made in the wall that had for centuries hidden the starry depths from us. It became clear that even the nearest stars are light-years away. To Alpha Centauri, 4.3 light-years. To Sirius, 8.2 light-years. So how far does all of starry space extend? Astronomers turned their attention to the Milky Way, that bright band encircling the sky, visible from both hemispheres. This indicated that the Sun and other planets lie inside a huge, flat system of stars. They named it the Galaxy. Democritus had guessed that it was a collection of stars, but only Galileo's telescope confirmed it. "I have observed the nature and substance of the Milky Way with my telescope," Galileo wrote, "so clearly that all disputes are resolved. The Milky Way is nothing other than a mass of innumerable stars gathered in clusters." In the 17th and 18th centuries, using telescopes, astronomers discovered many faintly glowing nebulous patches, nebulae. Matter could organize not only into stars and planets but into giant volumes of diffuse material. Thomas Wright first suggested that the stars of the Milky Way form a giant flat disk. William Herschel, with his sister Caroline, meticulously counted stars across the entire sky. The result of their 20 years of work was a map of the galaxy, showing its lens-shaped form for the first time. But it turned out that the Milky Way is far more complex. 20th century astronomers discovered that our galaxy is a flat, unwinding spiral of hundreds of billions of stars, with a bar in the center. The two main arms split into 5. The diameter of this behemoth is 100,000 light-years, and its thickness about 1,000. The Sun is located on the periphery, 26,000 light-years from the center, where a supermassive black hole of 4 million solar masses lurks. So, if you ever feel insignificant and peripheral, remember, even the Sun is just a provincial star on the outskirts of the galaxy. But that doesn't stop it from being the center of our world and the source of life on Earth. But is our galaxy the whole universe? Other nebulae of different shapes were visible in the sky. Some, even in powerful telescopes, looked like gas clouds rather than star clusters. William Herschel, with his giant telescope, spotted among them spiral structures similar to the Milky Way's, only very distant. But were they inside our galaxy or beyond? The answer came from Edwin Hubble. Observing the Andromeda Nebula, the previous method of measuring distances no longer worked. It was too far away. However, astronomers had found a new method thanks to a special type of star called Cepheid variables. These stars regularly change their brightness, they brighten, then dim in cycles. Astronomer Henrietta Leavitt in 1908 discovered that the maximum luminosity of a Cepheid is directly related to the period of its brightness cycle. That means, if you know the period, you can determine exactly how bright it is at its peak. This discovery allowed astronomers to measure distances to stars that are extremely far away. Hubble found several Cepheids in the Andromeda Nebula and calculated the distance to them. It was 2 million light-years, 20 times larger than the size of our galaxy. Thus, it was proved that the Andromeda Nebula is not some distant corner of the Milky Way but a completely different galaxy, possibly similar to ours. For the first time, it became clear that the visible universe is not just our star system. In the 19th century, the French philosopher Auguste Comte wrote, "We can imagine determining the shapes of celestial bodies, their distances, sizes, and motions, but we will never, by any means, be able to study their chemical composition, their mineralogical structure, or the nature of organic beings living on their surfaces. I maintain my opinion that any knowledge of the true mean properties of stars must forever be hidden from us." Strong statement, but science rose to the challenge, thanks to the birth of astrophysics. From distant stars, we can only observe and study their light. Newton had already shown that sunlight contains waves of different lengths, from red to violet. Astrophysicists learned to split this light into a spectrum using a spectroscope. The shape of the energy distribution curve in the spectrum allows us to determine the star's temperature precisely. By Wien's displacement law, the shorter the wavelength, the hotter the star. If the energy peak is in the blue, the star's temperature is about 20,000 degrees Celsius. Our sun's peak is in the green, corresponding to 6,000 degrees Celsius. Red stars are cooler, about 3,000 degrees Celsius. These conclusions do not depend on the distance to the star. Experienced astronomers can even estimate a star's temperature by its color. But how can we be sure the temperature obtained from the spectrum is correct? We can't fly to distant stars? Or can we? The temperature of a source has been tested hundreds of times in laboratories. The mathematics and logic of physics work unambiguously. If the predictions of theory agree with experiments, the theory is correct. Astrophysical methods give results that converge and also predict new phenomena. Any error would have been exposed long ago. Spectral analysis also reveals the chemical composition of stars through dark absorption lines. Each element leaves a characteristic set of lines in the spectrum, its fingerprint. The presence of hydrogen, iron, or calcium lines indicates those elements in the star's atmosphere. Their abundance can be estimated from the depth of the lines. By the way, this is exactly how we now study thousands of exoplanets. As I mentioned at the beginning of the video, another huge contribution came from the Zeeman and Doppler effects. It turned out that the spectral lines depend on the conditions in the source. Experiments showed that some absorption lines split into 2 or 3 under the influence of a magnetic field, the Zeeman effect. Detecting the Zeeman effect in the spectra of sunspots led to the discovery of magnetic fields on the sun. In 1842, Christian Doppler discovered the effect named after him. The pitch of an approaching train's whistle sounds higher, while a receding train's whistle sounds lower. This was confirmed by an experiment with an orchestra playing on a moving platform while musicians with perfect pitch stood on the platform and detected differences. A fabulous experiment, but what does it have to do with astronomy? French physicist Armand Fizeau proved that the Doppler effect applies not only to sound but also to light. If a light source is moving away from us, its spectral lines shift toward the red end. The amount of shift gives the speed of recession. Measurements showed that the lines at the eastern edge of the sun have a blue shift, and those at the western edge a red shift, confirming the sun's rotation and allowing its speed to be determined, matching the motion of sunspots. So by the early 20th century, astronomers had a powerful arsenal of methods to study distant objects. Giant telescopes equipped with spectrographs allowed them to determine composition, temperature, speed, magnetism, size, and mass of stars, not to mention the orbits and properties of even invisible planets around other suns. It seemed that the rapid development of science, mathematics, physics, chemistry, and astronomy had finally given humanity a clear picture of the world, with only details left to refine. But already in the 19th century, scientists began receiving signals that something was wrong with the picture of an eternal, unchanging universe. The first warning sign was the gravitational paradox. Think, if stars attract each other, why don't the distances between them change? It was thought that the attraction of an infinite number of stars from all sides would be balanced. But on closer inspection, that's not true. Gravity only works to bring masses together. Repulsion was not known then. So stars should inevitably fall toward each other, and the closer they get, the faster. In infinite time, they would have long ago merged into one supercompact ball. The paradox was resolved only when it was realized that stars in a galaxy move in such a way that their orbital speeds are high enough to avoid falling into the center. Everything that moved slower has already fallen into the supermassive black hole at the center of the galaxy. Bodies that move faster than the second cosmic velocity have flown away. Only objects with speeds between the first and second cosmic velocities remain in elliptical orbits. But neighboring galaxies mostly move toward each other. For example, the Milky Way and the Andromeda Galaxy are rushing toward each other and will inevitably merge in a few billion years. The paradox raised the question: if the universe is infinite and eternal, why haven't all massive objects already merged into one huge clump? With infinite time, any process should have time to complete. This paradox showed that something was wrong with the picture of an eternal and infinite universe. The second stumbling block was the photometric paradox, or Olber's paradox. Imagine you are in an infinite forest. Everywhere you look, there are trees. In an infinite universe, in every direction you should see a star. Then the entire sky would shine brighter than the Milky Way, with no dark spots. Even cosmic dust wouldn't help. Over eternity, it would heat up from starlight and start glowing itself. So the black night sky means there are gaps between stars, meaning the number of stars is not infinite. What a puzzle Olbers threw at us. But that was just the beginning. At the turn of the 19th and 20th centuries, a real revolution occurred in science. The discovery of X-rays, capable of penetrating opaque objects, overturned many principles of classical physics. The phenomenon of radioactivity was identified. Scientists penetrated the deep structure of matter and understood the arrangement of atoms, which the ancient philosopher Democritus had brilliantly guessed. Atoms turned out to consist of heavy, positively charged nuclei surrounded by light, negatively charged electrons. The nucleus itself contains protons and uncharged neutrons. Astonishingly, new scientific instruments could detect individual electrons, smaller than a billionth of a centimeter, and even study their properties. What progress! Even the nature of light was deciphered. James Clerk Maxwell created the theory of electromagnetism, showing the inseparable connection between electricity and magnetism. He condensed all known properties of electromagnetic phenomena into 4 equations. From them followed something astonishing. Light is an electromagnetic wave traveling through a vacuum at a constant speed. But what oscillates in a vacuum? The concept of a field was introduced. A magnetic or electric charge, as it were, endows each point of space with special properties of attraction or repulsion. These properties of the magnetic field are described by Maxwell's equations. And in those equations there was a mysterious constant, c-, the speed of electromagnetic waves in a vacuum. Remarkably, it exactly equaled the speed of light, 299,792 kilometers per second. Thus, the guess that light has an electromagnetic nature was brilliantly confirmed. This discovery just blew our minds. The universe turned out to be permeated by an invisible network of electromagnetic and gravitational fields. The propagation of light finally had a clear explanation. Photons are quanta of the electromagnetic field, its waves. They are the light that brings us news from distant galaxies. The world turned out to be invisibly richer and more complex than it had seemed just a short while before. Maxwell's theory, presenting the speed of light as a fundamental constant, deeply impressed a young Albert Einstein. In 1905, Einstein published a paper outlining the basics of the special theory of relativity. Motion is relative. All physical laws look the same for observers moving uniformly and rectilinearly, regardless of their speed. And the speed of light in a vacuum is constant in any frame of reference. That is, according to Einstein, all laws of physics are the same for observers moving uniformly and rectilinearly, and the speed of light is always constant. That sounds simple, but the consequences are wild. For example, if you throw a ball on a moving train, the speed of the ball is the sum of the train's speed and the ball's speed. By that logic, a laser beam fired from a spaceship should travel faster than light because of the ship's motion. But no, the laser beam will travel at the same speed of light as for a stationary observer, not a bit faster. That means time and distance flow differently for different observers. To explain this, Einstein proposed that the clock on the spaceship runs slower, and the ship itself contracts in the direction of motion. The crew wouldn't notice anything. For them, everything would seem normal. Sounds crazy, but experiments confirm it. Approaching and receding stars have the same speed of light. Clocks on satellites really do lag behind Earth clocks. So the world is not at all like Newton's, where time flows identically everywhere. For Einstein, space and time are relative. They depend on speed. He considered them a single whole, a 4-dimensional continuum. Only all 4 coordinates together, 3 spatial dimensions and 1 time coordinate, fully determine the location of an event in the universe. Now you know the secret of eternal youth. Just fly at the speed of light, though back on Earth. Nobody would wait for you. Relativity also showed that the speed of light is a limit. You can't exceed it. For example, if you weigh 70 kilograms and reach 90% of light speed, you would weigh 160 kilograms. At 99%, about 500 kilograms. If you accelerate another 1% to 99.99% of light speed, your mass would be 5 tons. As you approach light speed, mass grows to infinity. So speeding up more is impossible. Only gravitational waves and massless particles like photons always travel at light speed. But for them, time simply does not exist. Finally, Einstein lifted the veil on the nature of energy. It turns out that energy is not only mechanical work. There is also thermal energy and the energy of particle interactions. As Richard Feynman put it, there is a certain quantity called energy that does not change under any of the changes that happen in nature. It is essentially a mathematical principle that there is a numerical quantity that does not change no matter what. It is not a description of the mechanism of a phenomenon or anything concrete. It just notes the strange circumstance that you can calculate some number, then watch nature perform its tricks, and then recalculate that number, and it stays the same. Einstein derived his famous formula linking a body's total energy and its mass, E equals mc squared. The meaning is that mass is essentially a store of energy, an incredible one. Even a tiny piece of matter contains as much energy as an atomic bomb. 1 gram of matter holds 20 kilotons of TNT. To release that energy, you need annihilation, when a particle meets its antiparticle and they turn into pure radiation. Mass disappears, but many photons appear. By the way, 30 years after Einstein, his formula explained where stellar energy comes from. In the cores of stars, hydrogen turns into helium, but the mass of the resulting helium is slightly less than the mass of the original hydrogen. That excess mass becomes radiation, starlight. Every second, millions of tons of hydrogen burn away in the sun. But the real revolution in physics was brought by the general theory of relativity. Its essence is simple. Space-time and matter are inseparably linked. Masses curve space-time, and that curvature affects the motion of bodies and the flow of time. Sounds wild, but it's true. Imagine space as a trampoline. Put a heavy ball on it, it bends the surface. The heavier the ball, the deeper the bend. Now roll smaller balls across the trampoline. They no longer travel straight. They curve around the massive object, just like planets around a star. Because of the curvature of space, light rays also bend near massive bodies. Einstein predicted this, and during the 1919 solar eclipse, astronomers noticed that stars around the sun appeared slightly shifted. The sun's gravity was bending their light. The geometry of the universe is indeed non-Euclidean. And another surprise from Einstein: time flows at different rates in different places. The stronger the gravity, the slower the clocks run. On Earth, time lags slightly behind the moon. Hard to believe, but ultra-precise experiments have confirmed it. For instance, Gennady Padalka, who holds the record for longest time in space, 879 days, aged 0.02 seconds less than his twin brother on Earth. The difference is tiny, but it's there. So space-time is not a fixed stage but a living, moving actor. Masses bend space, and space changes the motion of bodies and the flow of time. Einstein instantly became a rock star. Time magazine's headline read, "Revolution in Science, the greatest achievement of human thought." But here's the interesting thing. General relativity did not cancel Newton's physics. It complemented it. At low speeds and small scales, their predictions are almost identical. But the stronger the fields and the faster the motion, the more important Einstein's theory becomes. He himself said that his ideas were a new level from which old physics can be seen as a special case. In short, Einstein didn't just rock the boat. His ideas continue to change our view of the world. Mass, energy, space, and time turned out to be inseparably linked in a single dancing tangle. And we are part of it. So next time you look at the stars, remember old Albert. As far back as 1783, the astronomer John Michel asked, "What if a star were so enormous that its escape velocity equaled the speed of light?" Calculations showed that then even light could not leave its surface. Michel called them dark stars. But scientists of the time lacked the knowledge to develop this idea. They didn't even know the exact speed of light. Only in 1916 did Carl Schwarzschild, using Einstein's theory, find an exact solution to the equations for the simplest case of a point particle, approximately describing the gravity of a spherical star. Schwarzschild's solution led to unusual conclusions. It turned out that an extremely massive star is surrounded by a magical sphere, now called the event horizon. Inside that sphere, no object can ever return. Approaching the horizon, an outside observer would see light circling around. Time inside the spaceship would seem to slow down and stop. For the astronauts themselves, nothing unusual would happen, except the sad fate of being torn apart. For a long time, everyone thought this was just science fiction. But in 1939, Robert Oppenheimer and his student Hartland Snyder proved that black holes can really form from massive stars that run out of fuel. They simply collapse under their own gravity and turn into black holes. Today, we know of at least 2 types of black holes: remnants of giant stars and supermassive monsters at the centers of galaxies. Astronomers have even found a black hole of 4 million solar masses right at the center of our Milky Way. If it weren't for dust clouds, it would shine in the sky brighter than the full moon. Creepy, right? But physicists didn't stop there. They applied quantum theory to black holes. Stephen Hawking showed that a perfectly black hole violates quantum uncertainty. Therefore, it must slowly emit radiation, Hawking radiation. Turns out that a vacuum is not empty but a kind of quantum soup. In the powerful field of a black hole, virtual particles are born. One may fall into the hole, the other escapes. That's Hawking radiation. Thus, black holes evaporate over trillions of years. So what happens to everything that fell into a black hole? In 1963, Roy Kerr found a solution for a rotating black hole. Turns out that it collapses not into a point but into a ring. Passing through that ring, you could enter a parallel universe or another region of our own, like a wormhole. These tunnels through space-time might connect distant regions or even different universes. Theoretically, you could travel faster than light without breaking the laws of physics. If wormholes ever allow us to zip across the galaxy, could they also let us travel back in time? For Newton, time was like an arrow, inescapable. For Einstein, it's more like a winding river, flowing at different speeds in different places. If we can move in 3 spatial dimensions, why not in the 4th time? What if there are whirlpools in this river that fling you into the past? Could it split into 2 streams, creating parallel universes? General relativity allows such possibilities. Hawking was so intrigued that he proposed the chronology protection conjecture, an undiscovered law of nature that forbids time travel. Otherwise, he joked, where are the crowds of tourists from the future at all the important historical events? Just imagine the chaos if we had a time machine. Everyone would get rich on Bitcoin, tell Nikola Tesla about wireless charging, try to persuade Van Gogh not to cut off his ear. Probably the most useless thing you could do. But then come paradoxes. What if you kill your own grandfather as a child? Where did you even learn the secret of time travel if you heard it from your future self? Can you become your own mother, daughter, and grandmother all at once? Like in Robert Heinlein's story? It seems only a theory of everything can sort this out. I have a separate video on that. Check it out on the channel. So all these mysteries of black holes, wormholes, and time travel will probably remain unsolved until we understand how quantum effects influence gravity and space-time itself. Only then will we know what awaits us beyond the horizon. Einstein was convinced of the stationarity and immutability of the universe, but his own equations led to the opposite result. The universe stubbornly refused to be static. To ensure the universe's stability, he introduced the famous cosmological constant lambda, a mathematical plug intended to balance universal gravity and prevent the cosmos from collapsing under its own weight. The physical meaning and nature of this anti-gravity remained a mystery. But galaxies hung motionless in space, so something must counteract their mutual attraction, Einstein reasoned. Another feature of his model was the finiteness of the universe. That is, if you got into a spaceship with infinite fuel and traveled to the edge of the universe, would you hit a wall with a sign, "End of the world"? No, space itself is curved and closed in on itself like the surface of a sphere. Flying straight, you would eventually return to your starting point. On the other hand, there are no edges. And although our world is enormous, it has a definite volume, just as the surface area of the Earth is finite though it has no boundaries. Einstein's theory greatly impressed the mathematician Alexander Friedmann. Analyzing the equations of relativity, Friedmann reached a sensational conclusion. They described not only a static universe but also non-stationary models, an expanding or contracting cosmos. In 1922, Friedmann showed that 3 scenarios for the evolution of the universe are possible, depending on the average density of matter. If the density is greater than critical, expansion will eventually turn into contraction. Galaxies will fly apart more and more slowly, stop, and then begin to approach with acceleration until they merge into a single point, a big crunch. At critical density, expansion continues forever but slows down. Galaxies coast by inertia, gradually weakening each other's attraction. If the average density is less than critical, the universe expands without limit, accelerating. In any case, the universe turns out to be non-stationary. Distances between galaxies do not remain constant. They either increase or decrease over time. In other words, the cosmos hasn't always been as it is now. Either these star islands somehow originated at colossal distances and are now slowly coming together, or they were originally much closer, even in a single point. and then some unknown force scattered them across space. In both cases, the universe clearly had a beginning, a moment zero when something grandiose happened. For the first time, the question of the beginning of the world was raised on a scientific level. And the first spoilers appeared, revealing the main plot twist of the universe. But as with any spoilers, many preferred to wait for official confirmation from the creators. Friedman's concept provided a simple explanation for the dark night sky. Light from distant galaxies simply hasn't had time to reach us. And as for gravity, its influence is limited either by the finite mass of the universe or by the high speeds at which galaxies are receding. They simply overcome gravity. Naturally, this theory spawned many new questions. What preceded the universe? Why did the Big Bang happen? How does the monstrous compression of countless galaxies into a point occur? And isn't the very birth of the universe an act of creation by someone outside? Friedman didn't know the answers. Einstein, although he recognized the mathematical correctness of his colleagues' calculations, did not immediately accept the idea. To resolve this dispute, empirical verification was needed. On Earth, you can't experiment with entire galaxies, but you could try to measure the speed of their motion using the Doppler effect, the shift of spectral lines toward the red, receding, or blue, approaching. In 1927, in California, Edwin Hubble set to work with the most powerful telescope of his time, a 2.5-meter reflector and modern spectrographs. This equipment allowed him to capture the faint light of distant galaxies and analyze their spectra for Doppler shifts. Hubble expected a chaotic pattern, some galaxies approaching us, some receding. But no, it turned out that the nearest galaxy, Andromeda, is indeed moving toward us at about 100 kilometers per second. But all the other galaxies showed a redshift, indicating they are moving away from the Milky Way. Moreover, a clear trend appeared. The farther a galaxy, the faster it is moving away. This became known as Hubble's law. The conclusion was unambiguous. The universe is not static. It is expanding in all directions. To better understand the expansion mechanism, imagine galaxies as dots drawn on the surface of a balloon. As the balloon inflates, the dots move apart from each other. The farther they were initially, the faster the distance between them grows. And it doesn't matter which point you pick as the starting point, the picture is the same. Could the scientists then determine the moment when all galaxies were extremely close, literally at a single point? Yes, Hubble's law allowed an estimate of the age of the universe, the time since moment zero. That age turned out to be in the range of 13.7 to 13.9 billion years. Nearly 14 billion candles on the universe's birthday cake. Looking for the point where all matter was assembled at moment zero is pointless. It's any point in the universe. So inhabitants of any galaxy can rightfully consider themselves the center of the world. Nicholas of Cusa and Giordano Bruno were right. The universe has no center. What was that moment? In your opinion, nothing? And suddenly a big bang, and out of nothing, from a point, the entire universe came into being? How can that be? If ancient thinkers speculated about the elements that make up the world, by the 20th century the chemical composition of cosmic bodies had become known. Spectral analysis of stars showed that they consist of two simplest elements: hydrogen, 75% by mass, and helium, 25%. All other heavy elements make up only about 1% of stellar matter. The same ratio turned out to be typical for the interstellar medium. Why is there 3 times more hydrogen than helium in the universe? Where did this proportion come from? German physicist Hans Bethe dug deeper and discovered nuclear reactions in the cores of stars, in which 4 hydrogen nuclei, protons, fuse into 1 helium-4 nucleus. That means if all cosmic helium came from hydrogen, there should be about 3 times less helium by mass. But there's a catch. The rate of these reactions in stars is too low. Over a star's lifetime of 510 billion years, nuclear fusion simply doesn't have time to significantly change the original composition of matter. It seems stars formed already from a mixture in which helium was exactly 25%. This was pointed out by George Gamow, a former student of Friedman. Combining the composition of the universe with the model of its expansion, Gamow realized that in the first moments after the Big Bang, the density and temperature of cosmic matter were so high that part of the hydrogen had already turned into helium. However, conditions were not right for the formation of elements heavier than helium. Thus, the theory of primordial nucleosynthesis was developed by Gamow and his graduate student Ralph Alpher. By the way, Gamow added Hans Bethe as a co-author after the article was written, just so the theory would be called Alpha Beta Gamow, Alpha Beta Gamma. What, you can do that? Moreover, Gamow, relying on thermodynamics, realized that at such high initial temperatures, matter must have been in complete thermal equilibrium with radiation. Calculations showed that in that primordial soup of hydrogen and helium, there must also have been photons, and by a huge margin, billions of orders of magnitude more photons than atoms. That's why heavy nuclei could not form. However, as the universe expanded, the energy density of radiation dropped faster than the mass density of matter. Gradually, the role of radiation in the dynamics of the universe became secondary. But where did those relic photons go? Gamow and his colleagues proved, nowhere. They are still here. Due to the expansion of the universe, the wavelength of those primordial photons has continuously increased. In the first moments after the Big Bang, they were superenergetic gamma rays. Today, they have cooled to microwave frequencies. In the mid-1960s, radio astronomers recorded a background microwave hum. But they didn't realize the significance of their discovery. Later, Arno Penzias and Robert Wilson, engineers at Bell Labs, were testing a receiver for satellite communications and encountered a strange microwave noise. It didn't depend on the direction of the antenna or the time of day. They tried everything: cooled detectors with liquid helium, even cleaned white dielectric material from the horn antenna. Nothing worked. That mysterious noise came from everywhere. Penzias and Wilson had become the discoverers of the cosmic microwave background radiation without even knowing it, and in 1978 they received the Nobel Prize for it. So the relic background produced by the Big Bang really exists. Its characteristics exactly match the predictions of Gamow's hot universe theory. It uniformly fills all space, confirming the homogeneity and isotropy of the universe even in its first moments. The microwave background arose only about 380,000 years after the Big Bang, when the plasma cooled and became transparent. The discovery of the relic radiation became, after Hubble's law, the second direct confirmation of the Big Bang concept. No alternative theories could explain this whole complex of facts. To avoid interference from Earth's atmosphere, detectors for the relic background were placed on satellites. The first such experiment, the Soviet Relict 1, took place in 1983 on the Prognoz 9 satellite, but its sensitivity wasn't enough to see the fine structure of the radiation. The breakthrough came with the American satellite COBE in 1989. It turned out that the cosmic microwave background is not perfectly uniform. There are tiny fluctuations in temperature and intensity. That means the young universe was not completely smooth. It contained minuscule inhomogeneities in density and temperature. That makes sense. Weak density fluctuations in the early universe should have been amplified by gravity, forming denser regions. The initial fluctuations, like snowballs, accreted surrounding matter. Thus, protogalaxies were born, and inside them, protostars, which then ignited. This idea seems logical, but when scientists try to describe it with math and physics, serious difficulties arise. First, the universe is constantly expanding, which reduces the density of matter. This expansion hinders matter from gathering into denser regions. How did tiny clumps of matter overcome the expansion to form galaxies? Second, in the early universe, it was so hot and dense that photons constantly collided with electrons, preventing the growth of clumps. Only when the universe cooled enough for electrons to combine with protons into atoms did matter become transparent, and clumps could grow. But calculations show that the clumps that could have formed then do not match what we see in the relic radiation. Something still doesn't add up. Ordinary matter made of protons and electrons cannot explain the structure of the universe. Something else is off. The answer came from an unexpected direction. It turned out that besides ordinary matter, the universe is filled with a completely different substance, dark matter. Its existence was independently deduced from anomalies in galaxy rotation. Astronomers had long noticed that spiral galaxies rotate strangely. The stars on the outskirts move as fast as those near the center, like a spinning wheel. To explain this, it was necessary to assume that the visible matter of galaxies is embedded in an invisible substance whose mass is 5 to 6 times greater than the total mass of all stars and gas. Galaxies are like icebergs, only a small part is visible. The lion's share of mass is hidden, revealing itself only gravitationally. This mysterious substance was called dark matter. But what is it? The possibility of invisible objects made of ordinary matter was quickly ruled out. Their mass is insufficient. It is much more natural to suppose that dark matter is a new type of fundamental particle. Apparently, these particles participate only in gravitational interactions, not in the strong nuclear or electromagnetic forces. Therefore, they cannot form atoms and do not interact with radiation. They freely pass through ordinary matter. Right now, dark matter is passing through your body. A bit creepy, isn't it? Physicists have coined a generic name for these particles: WIMPs, weakly interacting massive particles. The main candidates for WIMPs for a long time were hypothetical supersymmetric partners of ordinary particles, neutralinos. Alas, no traces of them have been found at the Large Hadron Collider. Now hopes rest on other options: axions, sterile neutrinos, and primordial black holes. In the early 1980s, Jim Peebles realized the cosmological role of dark matter. The temperature of the relic radiation reflects the distribution of ordinary baryonic matter in the young universe, but not of WIMPs. The latter had already begun to clump together under their own gravity. When baryons cooled and became transparent, they simply fell into the gravitational wells prepared by dark matter. Thus, dark matter clumps could develop unhindered, becoming the seeds of future galaxies. Eventually, visible matter settled into the potential wells of these seeds. Computer simulations of the universe's evolution, taking dark matter into account, gave stunning results. Theoretical calculations perfectly matched the data from the Planck satellite. Moreover, the simulations reproduced the honeycomb structure of today's cosmos. Galaxy superclusters form bubble walls, while the interiors of the bubbles are nearly empty. We really have understood how the present cosmic structures emerged from the homogeneous early universe. Now the task is to catch dark matter particles in experiments that would determine the specific physical nature of these elusive WIMPs. Although it cannot be ruled out that dark matter will turn out to be something completely unexpected. So the mosaic was almost complete. We had finally grasped the secrets of the universe. Most scientists were forced to accept the non-stationarity of our cosmos, some grudgingly, some with delight. To this day, there are people who deny the Big Bang, considering it a ridiculous invention of scientists. Some commenters still believe the Earth is flat. But even the hottest supporters of the Big Bang theory admit that it has serious problems. The biggest is the horizon problem. Recall that the cosmic microwave background is astonishingly uniform. Its temperature matches in all directions to within hundredths of a percent, and the tiny fluctuations are also the same everywhere. Imagine we point a radio telescope at one patch of sky, region A, and then at the opposite patch, region B. Why are the relic signals from A and B so similar? The distance between these regions today is about 90 billion light-years. They could never have influenced each other, because since the Big Bang, light has traveled only 13.8 billion light-years. Only points separated by no more than that distance can be causally connected. That's the horizon. How then can we explain the incredible uniformity of the cosmic microwave background in all directions? Even if A and B were much closer in the past, a signal still wouldn't have had time to travel between them. So A and B were never causally connected. Yet the conditions in them coincide with astonishing precision. What accounts for this fine-tuning? Another problem is the mysterious flat geometry of the universe. According to Friedman's models, the future of the world depends on the average density of matter. If it's greater than a critical value, gravity will eventually stop expansion and pull the universe back into a point. If the density is lower, expansion will be eternal. But the Big Bang could have produced any amount of matter and radiation. Why did the average density of the cosmos turn out to be so close to the critical value? The chances of such a coincidence are vanishingly small. At critical density, the universe has zero curvature and infinite volume. That's flat geometry. What perfectionists so carefully tuned the initial conditions so that billions of years later the density would be close to critical to within 15 decimal places? If we assume that in the first moment the universe expanded not by inertia but with acceleration, that would solve the horizon problem. Then a causally connected region could have expanded to become the entire observable universe. But what could have driven such accelerated expansion? A clue came from Einstein. Remember the cosmological constant? That anti-gravity he introduced to make the cosmos static. He called it his greatest mistake. But later scientists wondered, if something like that really existed and if it outweighed ordinary gravity, the universe would expand with acceleration. In 1917, the astronomer Willem de Sitter considered a model of an empty universe containing only the cosmological constant and showed that in such a world, two bodies would accelerate apart, the acceleration being greater the farther apart they are. So this force does not weaken with distance. It grows. Is this the key to the accelerated expansion of the early universe? Neither Einstein nor de Sitter could say what exactly creates anti-gravity. It seemed to be a property of space itself. So we again have to revise the idea of space as something empty and passive. We already know that the cosmos is filled with fields. Any point, even empty, can attract or repel particles placed there. Fields, and with them, space, contain energy. What used to be called emptiness, physicists call vacuum. But that's by no means a synonym for nothing. Vacuum is an active medium permeated by energy-rich fields. And it is probably the energy of these fields that provides the anti-gravity causing the accelerated expansion of the universe. So the key idea of cosmic inflation is this. Immediately after its birth, the universe underwent a brief period of extremely rapid exponential expansion. This initial inflationary phase lasted an inconceivably tiny fraction of a second, but during that time, a tiny region of space, 10 superscript 3 centimeters across, expanded by 27 orders of magnitude, reaching about 1 centimeter in diameter. According to the inflation hypothesis, first proposed by Alexei Starobinsky and then developed by Alan Guth, the cause was an exotic state of matter, the high-energy vacuum. Unlike our familiar vacuum, this initial vacuum had a colossal energy density. Each cubic centimeter weighed as much as the moon. Such a supervacuum generates a giant negative pressure, anti-gravity 3 times stronger than ordinary gravity. Under the influence of this anti-gravity, any lump of the high-energy vacuum begins to expand. But the initial vacuum is unstable. It inevitably decays, transitioning to an ordinary state with lower energy density. By Einstein's formula E equals mc squared, the excess energy is converted into the mass of elementary particles, quarks, leptons, photons, etc. So the high-energy vacuum evaporated, giving birth to the familiar matter and radiation of the early universe. That decay is what we perceive as the Big Bang. In that giant flash, nearly all the contents of our world, nuclei, electrons, neutrinos, quanta of light were born. And with that, the anti-gravity of the high-energy vacuum ended, yielding to the ordinary gravity of the newly born particles. However, the enormous inertia of inflation did not disappear, and the expansion continued, though at a slower speed. Continues to this day. Inflation elegantly solves the puzzles I mentioned earlier. The horizon problem, the uniformity of the universe, disappears because in the inflationary scenario, different regions of our universe did indeed share a common past. They were close together inside a tiny bubble and were later carried apart to enormous distances. The flatness problem is also resolved. Inflation was so powerful and fast that we simply don't notice the global curvature of the world. Just as an ant doesn't feel that it's crawling on the surface of a straw. As we already learned, to measure distances to nearby galaxies, Hubble used the method of standard candles, objects of known luminosity, namely Cepheid variables. But how do you determine distances to faraway galaxies that appear only as faint smudges even in the best telescopes? New beacons were needed. In 1977, astronomer Yuri Skovsky proposed using type Ia supernovae for this purpose. They occur when a white dwarf undergoes a thermonuclear explosion. This is perhaps the most dramatic way to announce your existence. The luminosity of such a supernova rivals the combined light of billions of stars in a galaxy. They are rare, but in the vast volume of the visible universe they go off often enough. In 1998, Brian Schmidt and Adam Rees published stunning data on 16 supernovae. It turned out that their brightness was lower than expected for their measured redshift, meaning these galaxies are farther away and receding faster than Hubble's law predicts. The acceleration graph clearly curved upward. A year later, the group led by Saul Perlmutter confirmed this result with dozens of supernovae. Something was definitely accelerating the expansion. An anti-gravity force, growing with distance, is acting in the universe. In 2011, Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics for this discovery. This fact fundamentally changed our view of the world. Previously, the debate was only whether there was enough gravity to stop expansion and cause a collapse. Now it became clear that expansion will be eternal, due to the dominance of anti-gravity. Galaxies will continue to fly apart, losing the ability to see each other. So what causes this acceleration? This unknown force was named dark energy. Early hypotheses about its nature used insights from inflation theory. Remember how after the Big Bang, the superenergetic vacuum turned into an ordinary vacuum with zero or negligible energy density. The accelerated expansion hints that the energy density there is actually a bit higher. That seems to be dark energy, or Einstein's cosmological constant. In this model, it uniformly fills the entire universe, both intergalactic voids and the interiors of stars. Its density is constant in space and time. It does not interact with matter. Calculations show that about 7 billion years ago, the average density of matter dropped below the vacuum density. And since then, the universe has been expanding with acceleration. The modern cosmological inventory gives the following composition of the universe. Dark energy about 70%, dark matter about 26%, and all ordinary baryonic matter just 5%. Amazing astronomers for 2,500 years have been studying only 0.5% of the mass of the universe. But what exactly are dark matter and dark energy, which make up most of our world? Strictly speaking, we don't know yet. But right now, scientists are working on hypotheses that will likely soon shed light on this as well. We are lucky to live in a unique era. The universe is cooled enough for complex structures to form, but has not yet fallen silent. So what awaits us in the future? Expansion will continue forever, accelerating to a limit set by the density of dark energy. Galaxies will recede until they become inaccessible islands of light. The last stars will burn out, and the cosmos will sink into twilight, illuminated only by rare supernova flashes. After an unimaginable quintillion years, even black holes will evaporate and turn black, leaving the universe cold and empty. Of course, this is still a scientific model, not firmly established facts. But this is the picture modern cosmology paints, the fruit of centuries of work and insights by thousands of scientists. And who knows, perhaps our intelligence arose just in time to peer into the abyss of the future and find a loophole to somewhere else. So where did that bubble of superplasticity come from? If you could peer into the vacuum at the smallest possible scale, about 10 superscript 3 centimeters, you would see virtual particles being born and disappearing in every point of space. Ghostly portions of matter, reminiscent of the motivation to exercise every morning. Usually, these particles almost instantly annihilate, emitting quanta of light. But if a sufficiently powerful field is nearby, it can separate the particles before they vanish. Then they become real, essentially arising from nothing, though actually created by the energy of the external field. In the quantum foam, various particles can arise, including those corresponding to the unstable vacuum. It takes only one fluctuation for the inflationary energy of the vacuum to unfold a pocket of spacetime into an entire universe. Such an event is unlikely but not impossible. But how does a tiny particle hold enough energy to become the mass of a Big Bang? For clarity, recall black holes. From the outside, they look compact, but inside they hide a monstrous store of mass energy. Gravity once collected and compressed matter into an extremely small volume, pumping colossal energy into it enough to warp and tear the fabric of spacetime at that point. So even if an object looks tiny from the outside, the internal geometry of its spacetime can accommodate an entire universe with enormous energy. Perhaps our cosmos is just the interior of a black hole in an unknown external world. That's not ruled out, though not proven. In principle, a supermassive particle called a Friedmann could also hide a vast universe inside. To an outside observer, such an object would look like a negligible fluctuation, though by its own internal clock it could live for trillions of years. So it's not impossible that even now, in our universe, microuniverses are being born. As paradoxical as it sounds, this is possible. You might think, are you feeding me nonsense? But physicists take this absolutely seriously. One of the scenarios for the origin of universes was proposed in 1983 by physicist André Linde. According to his theory, a rapidly expanding parent universe continuously gives birth to similar microuniverses, and the distances between them instantly become enormous. The result is an infinite family of worlds, each of which can further branch in its own accelerated expansion. In such a model, universes could be countless. Then our cosmos is just one bubble in a giant foam, a multiverse of infinite diversity and parallel worlds. The idea of a multiverse explains why life was able to arise at all. If you consider all possible variations of fundamental properties, from particle masses to cosmic constants, almost all of them are incompatible with our existence. The slightest deviation from current parameters would make the universe lifeless, lacking even atoms, stars, and planets. It seems as if someone carefully tuned the cosmos for future observers. You could imagine a higher civilization that programmed our universe by starting inflation from the right lump of vacuum. It's not impossible that someday Earthlings will learn to program microuniverses through controlled collapse of matter. There is another explanation. If the multiverse generates all possible combinations of fundamental properties, then among that variety, there will inevitably be improbable variants like our world. Somewhere, a random fluctuation will produce a set of physical parameters perfectly suited for complex structures, stars, planets, galaxies, life, and intelligence. So there is nothing surprising about our universe being so friendly. If it were different, we wouldn't be here to wonder at it. The multiverse idea truly amazes the imagination. There is a chance that somewhere out there exists an immortal version of me in our universe. I'm still working on that. However, not all scientists share the multiverse concept. Any good hypothesis should offer a way to test it by experiment. But parallel universes, by definition, cannot influence ours, so their existence is fundamentally unprovable. No real experiment can detect neighboring worlds. So should we even talk about them seriously? On the other hand, in recent years, scientists have increasingly encountered hypothetical objects that do not directly contradict physical laws but are inaccessible to experiment: dark matter, primordial black holes, wormholes. These are also entities beyond direct verification, at least for now. The idea of a multiverse and multidimensional spacetime should be taken as a promising proposal for the future. Right now, supercomputers are running complex simulations. Telescopes tirelessly catch signals from the sky. Accelerators and colliders probe the depths of the microcosm. Scientists compare their hypotheses with measurement results, trying to feel their way to the truth. Step by step, science is approaching an understanding of the fundamental foundations of the universe. Still, skeptics won't quit. Scientists still know almost nothing about elementary things. What triggered the Big Bang? What came before? What is dark matter and dark energy made of? How many parallel universes are there? Should I take an umbrella? Yes, our knowledge is not perfect and not complete, but it is growing. Since the time of Giordano Bruno, the volume of accumulated knowledge has increased by orders of magnitude. We are already discussing hypotheses that try to explain dark energy and dark matter. We have proposed the idea of the multiverse. We ponder the paradoxes of the anthropic principle. These are still just hypotheses. Further research, if not tomorrow, then in 400 years will answer these and other, perhaps not yet posed, astonishing questions. Science will find the answers. The pace of scientific progress is accelerating. It's hard even to imagine what discoveries await our descendants in the coming centuries. They will look at the ideas of the 21st century the same way we look at the speculations of the Middle Ages, knowing full well that in a few decades, this video too will be hopelessly outdated. Fortunately, that's exactly how progress works. If you made it this far, you're a true cosmic traveler. Hit like, subscribe, and let me know in the comments what part of the story blew your mind the most. Stay curious, and I'll see you in the next episode.